So you talked a little bit about resonance in general chemistry, but resonance is a really big deal in organic chemistry. It can help us explain a lot of things about how molecules react and their structure and things like that. So in the previous video, you already reviewed a little bit about how to draw resonance structures. Now we're going to go into more detail. So in this video, we'll talk about when resonance is present, why we draw resonance structures, and then in the next video we'll go through in a little bit more detail some tips for how to draw resonance structures. So we can draw resonance structures if we have something called conjugation present. And conjugation is if we have 3 or more atoms in a row that all have p orbitals in the same plane. Okay, so 3 or more adjacent atoms with p orbitals in the same plane. Okay, so if we have our atoms, we'll have the p orbitals, and if they're all lined up in the same plane, that means that electron density can be shared between all of them. Okay, so we have shared electron density, which increases the stability. So let's look at some common patterns of conjugated molecules, and then next time, or next video, I'll show you some tips for drawing the resonance structures for each of those patterns. Okay, so one common pattern is if we have alternating pi, sigma, pi bonds. All right, so an example of that would be here, where we have pi, then sigma, then pi. Okay, so our oxygen, carbon, carbon, carbon are all sp2 hybridized. They all have that p orbital, and so we have 4 p orbitals here in a row that can share electron density. Another pattern that we see is pi, sigma, and then positive charge on carbon. All right, this is something that you probably haven't seen before this class. So we'll start with a pi over here, then a sigma, and then when carbon has a positive charge, it only has 3 bonds. So 3 bonds, that means it's trigonal planar. 3 bonds, sp2 hybridized, so it has that empty p orbital. Okay, so p orbital here, here, and there. All right, and then our last pattern that we commonly see, and these patterns we can see, so we're talking about small groups of atoms here, but we can put these together to form much longer chains of conjugation, and then also we'll see some examples where these different types are combined with each other. Okay, so our last one, or our small pattern, is pi, sigma, and then lone pair. Okay, so if we have pi bond, then sigma bond, and then maybe an oxygen that has a lone pair. So this is where it gets tricky, because we would normally think about this oxygen as being sp3 hybridized because it has 4 things attached to it. But it turns out to be more stable if it's sp2 hybridized. And one of those lone pairs is in a p orbital. Okay, and so then that can line up and share electron density across the 2 carbons and the oxygen. Okay, so those are our different types of conjugation that we see. And again, in the next video, we'll go through more practice of drawing the actual resonance structures instead of just the patterns like we did here. But now we want to talk about why do we actually draw resonance structures? So this example is showing the acetate anion, one of our more simple molecules in terms of resonance for organic chemistry. And actually, if you look here, we can find the pattern. Okay, so we have pi, sigma, and then lone pair. How did we know which things to choose? So how did we know that we're going to use a pi bond here and then lone pair here? Well, in order for a conjugation, we have to have that alternating pattern, right? So we can't use the lone pairs on this oxygen because they don't have that sigma bond space in between. That means that if they were in a p orbital, it wouldn't be able to line up with the other p orbitals. Okay, I know that's complicated. We'll be practicing more and more, and hopefully it will become clear. Okay, so back to the question at hand. Why do we actually draw resonance structures? Well, if we study the acetate ion, so for example, if we look at this electron density map over here, we learn a few things. First of all, our CO bonds are equal in length. And also, the oxygens both share the negative charge. So you can see that the negative charge is evenly spread around the oxygens and even a little bit to the carbon. So we can only explain that by looking at more than one Lewis structure. All right. So basically we draw resonance structures if one Lewis structure doesn't give us a full enough picture to understand the properties or the reactivity of the structure that we're dealing with. So to take this into a little bit more of a maybe relatable example, so again, if we think of these two resonance structures, they're showing us that the negative charge is shared between those two oxygens. So these are both two different pictures of the same molecule, right? And only together can we understand what the actual picture of the molecule kind of looks like. So we can think of the same thing about any photograph of a person or animal. So for example, this picture shows part of my cat's face. Her name's Olive. You can see she has the nice olive colored eyes. Okay, but it doesn't show everything, right? So we can't see in this picture that she has these very cute little chubby cheeks. All right, but if we just had the chubby cheeks picture, we wouldn't be able to see her nice green eyes. So these are both pictures of the same thing, right? And just like our resonance structures, they're also a 2D representation of a 3D object. But if we put these two pictures together, then we get a better understanding of what the molecule, or the cat in this case, that we're actually dealing with looks like.